Hi everybody, my name is Juan Ponce Hernandez. I am part of Microtechnologies Division at CDC Querétaro. In this poster session, I'm going to present the research work named Development of Silicon and Polymeric Microneedles for Transdermal Monitoring and Drone Delivery. So what is the reason to develop microneedles technology? According to World Health Organization statistics, about 22 million people around the world have diabetes mellitus. The majority are from incoming and middle countries. This tells us that there is a call to develop technological alternatives to help to improve the current therapies to treat public health illness. Microneedles are made by the dry etching process, which can be done through two principal methods, isotropic and anisotropic. Isotropic dry etching consists in exposing the sample to extraviolet gas flow, which etch in all directions, but some areas can be protected by the hard masks made of aluminum, among other materials. The anisotropic dry etching, based on the post-process, only etch in one direction, but at the same way to isotropic, the etching can be controlled by employing a hard mask. The hard mask consists in two films, 200 nanometers of aluminum and 1.2 micrometers of photoresist. It is important to mention that the hard mask must keep the same shape through all the process in order to avoid an overetch in the obelisk side wall. The resultant microneedles array are used as a master mold to generate a PDMS mold, and the process consists in cast the PDMS polymer into microneedles array and let them cure at 60 degrees in an oven. The core of the development of microneedles array is the dry etching process carried out by the ion etching equipment, which is based on the BOST process. The BOST process are divided in three steps: passivation, where a fluorocarbon-based protection film is deposited. After the passivation step is carried out to decrease the layer thickness into the bottom of the sample. Finally, an extraviolet plasma is generated to etch the silicon, and respect to the polymer needles, SU8 polymer is cast in PDMS master mold that is exposed with UV light to generate the shape of microneedles. As we can notice by the figure, we can microfabricate sharp tip needles with an average of 8 of 500 micrometers. As mentioned previously, it is necessary to select a material mask with low etching rate in order to withstand all the isotropic and anisotropic etching process. Once we have the silicon needle, a PDMS master mold is generated to cast in them the SU8 polymer. As a result, we have a silicon and polymer microneedles the same shape. Finally, the polymeric microneedles are functionalized with glucose oxidation in order to sense glucose. Microneedles present the capability to penetrate human skin without damaging the microneedle. We functionalize a set of microneedles by coating the needles with a thin layer of gold and a functionalization process with glucose oxidase and albumin. Once the microneedles were ready to sense glucose, we test in a cycle volt amperogram test, and for the results, we observe a characteristic glucose peak close to 0.4 volts when glucose is added to the solution. And in order to obtain device sensibility, we realized a chronoprogrammic test, and the result showed a stable signal with sensibility of 56 microampere per millimole and centimeter square. And finally, the authors are grateful to CONACYT for the seed and an intent project to funding the present research project. Thank you for your attention.